we have done in the last lecture. Okay. Yeah. So these are the things. Now let's take this inhomogeneous Maxwell's equation. They are important to us. Okay. So you can think actually there exists distributed dual tensor. This dual tensor and okay, dual tensor and this F. Okay, let's take this very equation. So operate this equation on by partial mu. That means I am differentiating it. Okay, let's differentiate this equation on both sides. Okay, let me write that equation. So what that equation means, it's something partial by partial x mu, f mu, that's equal to 4 pi by c g. Is it? So I have written that equation. Okay, now let's differentiate this on both sides. Okay, like this thing, partial by partial x mu. Okay, partial by partial x mu. So you have partial by partial x g. Okay. So now let's look at this very quantity on this very side. So this is a double derivative, is it? Is this a double derivative? Okay. Now you are having index nu and mu here, and you are having index mu and mu here. This very object, it's antisymmetric in mu and mu. Okay. So this is antisymmetric in mu and mu. What about this very objective? This partial 2 by partial x mu, partial x mu. What about this very objective? So this is same as what? Partial 2 by partial x mu, partial x mu. So it means it's what? Symmetric in mu and mu. Clear? Is that true? So because this is simply the double derivative, so I can interchange the partial derivatives. So it is like this thing. You are having partial 2 by partial x, let's say partial y. So you can write it same as partial y, partial x. Is it?
Yeah.
So that means this derivative, this double derivative is actually symmetric under the exchange of x and y. Clear? So similarly is here. So this means this object is symmetric in this mu and nu. Clear? So now tell me what this product will be. Now this object is this entire object. Okay. What it will be? So you are having this kind of situation here. So you are having a symmetric matrix A mu nu. Then you are having an anti-symmetric. So this is symmetric and this is anti-symmetric. Okay. So what this product is? 0. Okay. If you are having a quantity which is symmetric in some indices, multiply it with, okay, take an inner product with some another quantity which is anti-symmetric in the same indices. Okay. Then this product is 0. Okay. This we have done explicitly. Okay. So it means this left hand side is equal to 0. It is equal to 4 pi by c, okay, partial mu g. Or in other words, what we have, so we have this very equation. Okay, let me write partial mu g, that's equal to 0. Okay, mu is a domain index, replace it by mu. Okay, so that is same as partial by. So what does it mean? So this is actually the, okay, let's rewrite it. Let's write it in the three-dimensional form. What exactly this equation means? Let's get the meaning of this very equation. So if you see, it means that there is a conservation of something. If you are having, let's say, a d by dt of f that's equal to 0, then you can think f is a constant, is it? Clear? Or if f represents a dynamical variable, and if its time derivative is equal to 0, you can think that dynamical value is conserved. Okay, that quantity is a conserved quantity. So this means there exists a conserved quantity. Now let's figure it out, what exactly that means. Let's write it in the three-dimensional form. So let's sum. So it is partial x 0, like this thing. Then you are having partial by partial xi, ji, that's equal to 0. And here is a sum over I. some more I. It is I is what? A special index. Clear? So what is J0? Can anyone tell me? J0 is, yesterday we have written, J mu is equal to C rho times vector J, is it? So this is the charge density and this is the current density, okay? So this will be C partial rho by C partial T, okay? What about this thing? So this is simply, if you see, this is the divergence of J, is it? It is the dot product of this partial by partial xi with J, because I is contracted, so it is something del dot J, that's equal to 0. What you are having? Partial rho by partial T plus del dot J, that's equal to, what is this equation called? Equation of continuity. Okay, so this is your equation of continuity. So that means this equation represents what? Continuity equation. So when you are having a continuity equation, what does it imply? Conservation of charge. Okay, so let's write that. Okay, so let's define a quantity. Q is equal to integral d3 of x times rho. Okay, so what it will give me? Total charge. So therefore, let's integrate this equation over volume. Okay, over volume V. That's it. So this integration over volume V. So what I am getting? So you will be getting partial by partial T integration over volume rho. Okay, so that's equal to minus integration over volume V del dot J. Clear? So what this object is? So it is partial Q by partial T, that's equal to minus. Okay, what this is? So let's apply the Cos Divergence Theorem. So it will be integration over surface J dot. Okay? Samajh? Okay. So if you are having, let's say the volume is finite, the region is finite. Let's say a region is finite. Within that region you are having a charge, and the charge, there is a change in charge, okay? Amount of charge, huh? Samajh? Rate of, so this is what partial Q by partial T, that means charge in that very volume is changing, is it? So what happens to that? So this is a surface integral. So that means something appears on the surface. What will appear on the surface? That's current, is it? So in other words, you are having a flux density here. Huh? Across the surface, you will be having a flux. That flux here is given by the current density. Is that true? Because once the charge is changing in a given region, so the current will appear where? On the surface. Okay? You got it? Now, if my region tends to extends up to the boundary, okay? Let's say if the boundary extends to infinity, let's assume. Okay, since we are assuming at the boundaries there are no sources. Okay, so if this region, okay, if this s tends to infinity, that means, okay, let's say if x tends to infinity, okay, boundary is very large, okay, boundary is very infinite. What will happen to this very thing? Huh? So that means this very term will go to the 0. So it means, what it means then? So what it means? dq by dt, that's equal to 0 at the boundary. What it implies? Q is conservative. So it is still conservative here as well, because the change in charge, okay, rate of change of charge in a given region, that will across the boundary you will see as the current, okay, as a flux density, and that flux density will be represented by the current density. Clear? Samajh? Okay. So the amount of charge which moves out, okay, which is changing, that will simply appear as the current. This is also the conservation law, okay? Any question? Any question? Okay. let's look at this very quantity. I am having this partial mu j mu is equal to 0. So I have defined this very quantity. Q is equal to integration over volume. Okay. J0. What is J0? That is C times rho, is it? So let me divide this by 1 by C. J. So this is same as what? D3 of x rho. Is it same? Is it same? Okay. Now tell me if I am in the 4-dimensional space time. Okay. Let's assume we are in the 4-dimensional space time. What this volume will look like? What is the equation of this very volume? This 3 volume. So it will be simply a hypersurface while time is constant. Yesterday I have told you. Okay. So I can assume this volume. Okay. So this volume I can assume while you are having this. You define actually a hypersurface while x naught is what? Constant. If you are in the 4-dimensional space time, so if you assume a hypersurface while hypersurface kind of this thing, time component is constant. So what you will get? The projection will be on 3 volume. Simple this special volume. Okay. So in other words, I can write this object, this Q. So there, okay. So this quantity, this equation implies there exists a certain quantity which remains conserved. Okay. What we call as Q. Okay. This I define like this thing: some J mu or some hypersurface S. Okay. Let's assume you are having some hypersurface S. Okay, so this is this a scalar quantity? First tell me. Okay, now if I assume my hypersurface, okay, here let's say if I take hypersurface x naught equal to be constant, what this surface will look like? Since it is in the 4-dimensional, so what this surface will look like? It will simply give me the volume, is it? So if I take, so I am having this objective 1 by c integral j0. So ds0 will be simply what? D3 of x. Got it? So that means this very equation actually yields this kind of conservation law. Okay, it is not necessary you can choose conservation over actually hypersurface x naught equal to constant. You can be having other plane to be, let's say you can choose another hyperplane. Clear? But still you will be having a conservation law. Clear? So this is a very general way to define the charge Q. Okay. So over certain hypersurface, let's say I am taking hypersurface x naught equal to constant. You can choose some another thing. Okay. Then you need to define the volume. The remaining coordinates. Let's say if I am choosing x is equal to constant, then what will be the volume? What will be the okay? So if I take hypersurface x equal to constant, or let's say hyperplane x equal to constant, then that would mean actually the value y, z and t, is it? So then you need to integrate this very quantity over what? Y, z and t, okay? Accordingly, you need to choose the components, clear? Okay, so since we are only interested in x naught equal to constant hyperplane, so we'll use this thing, okay. Okay, along the same analogy, let's say if I am having some quantity T mu nu, some rank 2 tensor. Okay, so this is a rank 1 tensor, is it? Let's assume I am having a rank 2 tensor. Okay, and it's a conserved quantity. Rather, it satisfies this kind of equation. So you just differentiate. Okay, and that's such that this mu is contracted. One index remains as such. Okay, clear? So on the base, along this analogy, what there should exist a certain quantity which is conserved. Is that true? So what would be that conserved quantity? So I will take this T mu nu. Okay. So look here, you are having the contracted index mu, is it? So you contracted that index with what? Some surface. Okay. So what is the contracted index here? Mu, is it? So let's assume some hypersurface ds. So you will take that thing. So free index you will keep as such, integrate over this hypersurface. Okay, so that means this will imply a conservation of this quantity. Look here, in this very rule, okay, or in this very equation, you are having only one free index, is it? although you started with the two indices, but the conservation along mu index resulted in only a single index quantity, is it? So that means you need actually a conservation of a certain quantity which is having only one index, only one free index. Clear? So I have contracted, okay, one of the indices I have contracted over some hypersurface and rated it in this fashion. So that means this very object is a conserved quantity. Clear? Look here. So you are having only one index here. That is why. So this is a scalar quantity, is it? So it does not have any other free indices. Okay, so that's why you are having this Q. So this will result in actually the conservation of some vector quantity. So this results in a conservation of a scalar quantity. So this will result in what? Vector quantity. If you are having, let's say, more indices, so that will result actually accordingly the conservation of those type of quantities. Clear? Any problem? Okay, so this we will see in a moment, this kind of quantity. Okay? Before doing that, we will derive something. So this is the only portion. I mean next tomorrow's lecture will be the end of this tensor analysis business. Okay? Then we will do the same electrostatics what you have been doing all the time. Okay? Okay, so let's do something with some vectors. Let's take the Maxwell's equations. Okay, can you turn off the ACs and open the windows? It's very hot. Okay, so let's do some vector business. So you are having inhomogeneous Maxwell's equation like this. Curl of D, that's equal to 1 by C, partial E by partial T, plus 4 pi by C J. So this is Ampere Maxwell's equation. So then you are having this del dot E, it's equal to 4 pi. Clear? So also you are having these two equations. Curl of E, that's equal to minus 1 by C partial H by B. Okay. So let's take okay. So call this equation first, and this as equation second. So I will do this way. So let's take the dot product of E with this curl of B. Okay. It itself means it's a vector quantity. That's why I will not put. Okay. So 1 by C. So what it will be? E dot partial E by partial T. So you cannot take E directly inside it, okay, because it's a time dependent quantity. 4 pi C E dot G. Okay. Then with this thing, what I will do, okay, so let me take this very equation third. With equation, so this is from equation 1. So from equation third, so I can have D dot curl of E is equal to minus 1 by C B dot partial E by partial. Okay, so now let's subtract the two. So you just E dot curl of B minus, okay, so I am subtracting the two, so D dot curl of E is equal to 1 1 by c. Okay. Now if you look here, okay, so it's E dot something. What I will put, I will take this E inside this partial derivative and divide by 2, like this thing. So 1 by c, 1 by 2, partial E square by partial t. Can I do it? So once you differentiate it, so it will be E dot this thing. Since E square is actually E dot E. Okay? So you can then plus 4 pi by c E dot j minus and minus is plus, so it's 1 by c. Similarly, I can write it partial by partial t b square. Okay? So what we have used, partial E square by partial t, that's equal to twice E dot partial E by partial t. So E square is actually E dot E. Huh? So now can you tell me what this object is? So there is a identity and divergence of A cross B. Okay, let's use this identity. So it is B dot curl of A minus A dot curl of. Okay, so this is a standard identity. So now let's apply it here. So let's take E to be A and B to be B. So then what it will be? So there is a minus sign. So this, okay, so I'll be having, so this equation yields me minus times del dot E cross B. Okay, because I'm taking, okay, now apply here. So this is A, this is B. So you will be having the minus sign because this is a minus here. Right? So that's equal to 1 by 2c partial by partial t. Let's club the terms of fields by this thing. Then you are having an object 4 pi by c E dot j. Okay? Clear? Okay. Okay, so let's write. So I will put it this way: partial by partial t E square plus B square divided by 8 pi. Okay, so this is the way. So that means I am taking this 4 pi common. Okay, then so it's equal to, anybody? It will be something minus j dot E. Okay, so this is j dot E. So then I will take c divided by 4 pi. So minus c by 4 pi, then del dot E cross. Okay, so this is our equation, final equation. Now we define a quantity. Okay, quantity S that is defined at c by 4 pi. It's a vector quantity E cross B. So this object we call as pointing to. Okay, so this is an electrostatic unit, sir. So this is actually the pointing vector E cross B. Samashavan? So we'll figure out the interpretation of this pointing vector in a moment, what it represents. So I can write it partial by partial t E square plus B square by 8 pi. It's equal to minus j dot E. What is J? It is the 3 current density. Okay, minus del dot. Okay. Okay. So now let's integrate this over value. Okay, integrate this very equation over value. Volume B. So what I will get? So it is integration partial by partial t of like this in E square plus B square by 8 pi dV. Okay, then what I am having? Minus integration of volume V j dot E dV, then I am having minus integration of volume del dot S. Clear? So this is simply, I have put the integration here. Okay, now let's apply the Cos Divergence Theorem on this very thing. So this is del dot a vector, is it? So we can convert this, okay, to the surface integral, applying Gauss law. Okay, so how it will look like? So it's minus integration of volume J dot E dV minus integration over surface S. So it is S dot. Let me call surface to be F. So F is a surface, because S I have used it for the pointing vector. So it will be like this. Clear? Got it? Okay. So now if my this boundary extends to infinity, so what will happen to this thing? Because this S contains the fields E and B. Okay? So it means since at the boundary we are having fields vanish. Clear? So it means, okay, if let's say F tends to infinity, that means the boundary extends to infinity, where field vanish, so it implies this object is vanished. Clear? Got it? So now we are on the boundary, and the boundary is where it extends to the infinity. Clear? So in that case, what I am having this partial by partial t integration over this object by 8 pi. Okay, let me simplify this very term in the moment, then I can write together all the terms. Okay, so what is this J? Okay, integration over J dot E. Can you tell me how I can write in the discrete form? Since this is integration over volume, is it? So how I can write it in the, let's say you are having now point charges. Let's consider the point charges. Okay, point particles carrying charge E. How I can write it? Yes? So how I, okay. So let's say how I write this J, current density, for the single point charge. Yes? So if let's say if you are having a charge Q, okay, and that charge is moving with the velocity V, okay, then what it will represent it?
In the area.
Huh?
In the area. DA.
Yes. बताइए.
Multiple इसको करेंगे DA से.
Will it represent now the current density? Okay, I need to put actually rho, is it? Rho times V, okay? Is it? So I need to put actually rho times V. Rho into V will give you what? A current density. Or if I put in this fashion, E times, let's say N is the number of charges and multiply with the velocity. Let's say Q is the charge and N is the number of charges. Okay? So multiply with velocity. Does it represent something?
Yes.
It represents the current density, is it? So this is the number of particles per unit volume, you can think. Okay? So does it represent the current density? Does it represent? Agreed with it? Now tell me how I can write this J dot E now. Now tell me. So it is V dot E, is it? So I will write sum over all particles. Okay, like this thing. Q into V dot E. Can I write it? Because there is a volume element already here, is it? So that volume element, if I write this as rho times V, let's say if I write this in this fashion, rho times V, what that is actually? What this rho is? It contains a charge. Okay, let's take the dimensional. So it contains a charge by certain volume. Okay, multiplied by the velocity, is it? So this volume, dimensionally, this volume and this volume will go. Okay. So ultimately, what you will be getting here? Q into V dot E. But this we have considered only for a single charge. So what you need to do? Sum over all the charges. Clear? So that means this very object will be what? So this J dot E dV will be like this thing. Clear? Okay, so I have given you the home assignment some time ago. So if you are having, let's say, this epsilon is the total energy of the system, total mechanical energy. You remember? Mechanical energy. Okay, then this dE by dt, that's actually equal to Q into V dot E. Let's write this as mechanical energy. Okay, a particle is moving. So let's think of this we did in the relativist case. It's true for the non-relativist case as well. This very equation. You remember it? You remember this identity? Huh? So when we were trying to figure out what is the amount of work done by a charge in electric field and the magnetic field. In case of magnetic field, we found it is equal to 0, but it's only the electric field where we can do certain work. Okay? So that's actually equal to what is the velocity multiplied by the electric field. Clear? So that means this very object I can write as, okay, sum over all particles d mechanical by dt. Clear? So it means, let me write it in this fashion, d by dt of epsilon total. Okay, but that is the total mechanical energy of the particles. Okay, so can I write it in this way? So therefore, let's write, I can have therefore this partial by partial t e square plus these scholars are not staying at the one place, they are making noise all the time. Okay, so I can write it in this way, minus, what is this thing? So it's d, okay, d by dt of total mechanical energy. Okay, that means this means the rest mass energy, this mechanical energy, the rest mass energy plus the kinetic energy. Or you can take the kinetic energy of the particles. Because we are considering the particles are moving, so you can consider the, this will simply represent the what? Total kinetic energy of all the particles in a given system, okay, or in a given region which we are considering. Clear? Okay. So this equation I require in a moment. Okay, so you have written it? Huh? So let's try that. So I write d by dt like this thing. So there is an integration. This thing. So this object e square plus b square divided by 8 pi dv plus. So that's equal to 0. What it gives me? What it gives me? So that means there is a conservation, is it?
Yes.
So summation what? So it means this entire object is conserved. So it's a conserved quantity. Now tell me, so this is this mechanical energy entirely corresponds to the energy of the particles. It does not correspond to the field. Clear? Summation? So because it does not contain field. So what is the formula? So this, for the relativist case, this mechanical energy is simply what? mc square divided by root of 1 minus v square by c square. Okay, if I am considering the relativist particles. Otherwise, it will be simply kinetic energy plus potential energy of the particles. Clear? Now, samajh aa? So this is okay. If this is energy, what this should be? This is energy as well, is it?
Yes.
Samajh aa? If you are having a closed system, let's say, okay, let's assume you are having a closed system where you are having particles carrying the charge, okay, clear? So when you are having particles carrying the charge as well, and there is a field, so this region contains the field. So this equation means the sum total of energies pertaining to the field and the charges, okay, or the particles remains conserved. That means total energy of the system is conserved. Okay, so this is the energy contribution from the fields, and this is the energy contribution from where? From the particles itself. Clear? So we call this object, so we write, let's say, E to be the energy of the field is 1 by 8 pi integration E square plus B square. Okay, so this is the energy due to, okay, due to EM field. So in other words, I can have this, okay, let me write energy density. So that's equal to E square plus B square by 8 pi. So this represents energy density of the field. Clear? So this gives me the conservation law. So what we have considered? We have considered actually a very large region, okay, where we have assumed at the boundary of that very region fields vanish. Clear? But it is possible we can consider actually the finite region. Let's consider the finite value. Okay. Okay, let's assume the finite value. Okay. So, assume finite region. Okay, so which implies, which means this object S dot df does not vanish because this we suppose it to vanish at the boundary, but now the region is finite, okay, and the boundary does not extend to infinity. Why you are late?
So I missed my bus.
Okay. So let's rewrite this very equation. So you are having partial by partial d integration over volume E square plus B square by 8 pi dv. So what this object is? Minus partial by partial t. So it gives me the mechanical energy total mechanical minus x dot d. Okay, so let's rewrite it. So I'm having the partial and partial t. Okay, so this quantity I assumed what? Sorry, this quantity I called the energy of the field. Okay, so let's write that as E plus. So since we are using E to be electric field, okay, so I should not use E. Let me write the quantity itself. So you should choose some another variable for it. Let's write fancy E. Fancy E to be the energy. Energy of this very system, or simply W. Let's write W to be the energy. Okay, then plus this total mechanical energy, it's equal to S. Yeah. S. Okay, it's very unbearable. Okay, so now let's interpret it. What this means? So our region is, okay, it's a finite region. In this region, what is changing? So left hand side gives you the change in energy, is it? So and you are having the right hand side, it's an integral defined on the boundary, is it? So then what this should give me? So if you are having energy is changing in this very region, let's say in this region energy is changing. When you look at the surface, what will happen? How you will see it at the surface? It will be simply the energy flux through the surface. When something is changing within the surface, so across the surface it will be, something will be coming out of the surface. That we call as the flux, is it? Or rather the flux density, okay? So that means this very quantity, okay, along this very surface, let's assume, okay? So that means, so this S should represent actually the flux density. What kind of flux? Energy flux density, clear? So that means pointing vector represents me the energy flux density. Okay, that means it simply gives me the rate of, okay, change in energy across a boundary per unit time. Okay, clear? So this is the interpretation of the pointing vector. Okay, so this is actually the continuity equation for the energy density. Huh? Okay, so let me write what it means. overhang, okay, on LHS. What overhang on LHS? We have change in the total energy of the field and particles. Okay. Therefore, S dot df, okay, over this must be interpreted as the flux of energy across the surface. Across the surface, okay, bound surface F, bounding volume. Okay, so this is volume V, and you are having surface F here, okay? So that pointing vector S is this what means that the amount of energy passing through unit area of the surface. Okay. So this is the interpretation of what? Pointing vector. How much time is remaining? Oh, you said we still have a lot of time. Okay. So let's derive something. Let's derive the Euler-Lagrange equation for the fields. Okay, we know Euler-Lagrange equation. So let me write. So this is the Euler-Lagrange equation what we know. Partial L by partial Q dot minus partial L by partial Q is equal to 0. So what is our Lagrange? It's simply the function of Q and Q dot. Clear? Oh, it's very hot inside, right? Yeah, sure. So somebody accompany him. So let me stop here.